So, as Carolina said, my name is João Novo, and today I will talk to you about effective 2D metrics and how we can use them to study the circular geodesics of generic spacetimes. But before I begin my presentation, I would like to thank the organizers, in particular to Professor Luis Crispino, who is not in the room but hopefully is watching, for giving me the opportunity of presenting this work, which was done in collaboration with Professor Carlos Herdeiro and Pedro Cunha, my advisors for my PhD at University of Aveiro. So this is the plan of my talk. I will begin by motivating the study of circular geodesics and why we should study them and why they matter. Then I will hopefully teach you how to construct effective 2D metrics which describe the geodesic motion on generic spacetimes, which are four-dimensional Lorentzian metrics. Then I will relate the geometric quantities of these bidimensional metrics to the existence and stability of the geodesics we are considering, the light rings and the marginally stable circular orbits. In the end, I will try to put a spin on this formalism by considering rotating spacetimes, which is not trivial, as we will see. So, why geodesics matter? Well, I lost my presentation, but geodesics matter because we are working in general relativity. And as John Wheeler said, spacetime tells matter how to move, and matter tells spacetime how to curve. And we will focus on the first part of this sentence. Spacetime tells matter how to move. And what does spacetime tell matter then? Well, it says, follow my geodesics. This is the geodesic postulate that states that an accelerated test particles will follow the geodesics of the spacetime. In particular, there are two important classes of geodesics. The null geodesics, when we are considering the circular ones or spherical ones, describe the shadow of black holes, which can then be constrained by observations like the Event Horizon Telescope. And when we are considering time-like geodesics, of particular importance orbits are the ISCOs, which determine the accretion disk dynamics around black hole spacetimes. So, having defined why geodesics matter, we can start to construct the effective 2D metrics, which we will use later on. So, before we do that, we have to state which kind of spacetimes we are considering. And we will be considering spacetimes that are static, spherically symmetric, asymptotically flat, and 1+3 dimensional. Under these conditions, any generic spacetime can be written with the following line element, where d omega square is the usual line element on the two-sphere. We will further require the metric functions f and h to be at least C2 smooth. That means their first and second derivative is continuous. And we will considering spacetimes of this form harboring both black holes and horizonless compact objects. In the case of black holes, we want them to be non-extremal, meaning that they have a strictly positive surface gravity. And in the case of horizonless compact objects, we want them to be regular at the origin, which constrains their Maclaurin expansions of the metric functions f and h of r, like this, and we have no linear component, no linear coefficient on this series expansion. So now, how can we extract the metrics? We want metrics that describe the geodesics of the spacetime, and we know that the geodesics of the spacetimes can be obtained by the Hamilton-Jacobi equation, which has this form in very compactified notation. If you use the line element I showed you before and expand this expression, I don't know what this is happening, but if we expand this expression, what we obtain is this one. And by inspection, we can see that we can recast this equation in this following form, which allows us to define a new metric which is bidimensional and has the same geodesics of the spacetime. It will be this metric alpha ij here. And this allows us to define a line element. And this metric alpha ij is known as the Jacobi metric. It describes a two-dimensional Riemannian manifold, which is energy dependent, and whose geodesics are the spatial projection of the spacetime geodesics. And this is done, this is done on the equatorial plane because we are in spherical symmetry, so all geodesics are planar. So to have a grasp of what these effective 2D metrics are, I will give you the simplest example. When we start by taking the null limit of vanishing mass, which yields this Jacobi metric. But since the energy is a constant, we can redefine the parameter to observe it, and we obtain this expression here. This is widely known in the literature. It's called the optical or Fermat metric and has been used several times before for gravitational lensing, the study of shadows, even the study of general properties of near-horizon geometries, and even for black hole spacetime, for double black hole spacetimes. So let's consider now the simplest black hole we know, which is the Schwarzschild one. It has this line element, which yields this optical metric for Schwarzschild. This optical metric, which is bidimensional, describes a surface of revolution. This means that we can embed this surface on Euclidean tree space. It has this form, and we can see that is a surface of revolution because we have a line that is revolving around the central axis. And here the radial coordinate grows on the up direction. Grows upwards. And when we have spherical surface of revolutions, the parallels, that is curves with constant radius, are geodesics when they are extremal circles. And what I show here in red is the light ring located at 3M, the usual light ring, and it corresponds to a minimal circle around the surface of revolution. And what we know then is that the optical metric for Schwarzschild is the induced metric on the surface. I hope this has given you some kind of insight on what these metrics represent. So now I will give you a brief course on differential geometry to tell you how we can study these manifolds, these 2D manifolds. We'll be concerned with curves, which will be the geodesics. To do so, we will study their geodesic curvature, which has this expression here in terms of the vectors, or this one here in terms of components, which is probably more familiar to you. But in terms of vectors, t is the tangent vector to the trajectory, n is a normal vector to the manifold, and lambda is the parameter along this geodesic, or along the curve, not necessarily a geodesic. And this measures the failure of a curve to be a geodesic, and it vanishes when we have a geodesic. But we will not only be interested in the properties of curves on this manifold, but also on the intrinsic properties of the manifold, namely its Gaussian curvature, which is defined here as the product of the two principal normal curvatures. This might seem a little bit abstract, but I will give you two examples to give you a grasp of what we are talking about, and those two examples will be the sphere and the plane. In the sphere, all points are the same, and all geodesics are the major circles, which have curvature 1 over r. And so the Gaussian curvature will be positive and be 1 over r squared. When we are in flat space, the geodesics are the straight lines which have 0 curvature, so the Gaussian curvature of the plane is 0. This is expected because the plane is plane, so it has vanishing curvature. But what we can see from these two examples is some kind of behavior. For example, if we start at a point, at a sphere, and draw two geodesics that pass through that point, they will meet again on the opposite pole. So they start diverging, and then they will converge again on the opposite pole. Whereas in the flat case space, the geodesics will never meet again. And this can be made more formal, but what I'm trying to say is that if the Gaussian curvature is positive, geodesics that start nearby will start to approach eventually, and if the Gaussian curvature is negative, they will grow further and further apart. So the Gaussian curvature will determine the stability of the geodesics we will be considering. So what I want you to take home from this brief course on differential geometry, which I call the briefest course on differential geometry, is that the geodesic curvature will tell us if a curve is a geodesic, and the Gaussian curvature will tell us its stability. So now we can start to study the geodesics. We will begin with the simplest case, the null geodesics. So the null geodesics, we know that for the curves to be a geodesics, it has to have a vanishing Gaussian geodesic curvature. And if we compute the stability for curves that satisfy this condition, what we obtain is this expression for the Gaussian curvature. This term will be always negative, and this will depend on the slope at which the geodesic curvature crosses the horizontal axis. So what we know from this is that imagine that we have this plot of the geodesic curvature, and if we have a zero, which is being crossed with positive slope, this corresponds to an unstable light ring, and if the zero is crossed with negative slope, we have a stable light ring. Now, we want to establish some sort of theorem like what Pedro did before on the existence, number, and stability of light rings in generic spacetimes. To do so, we have to study this function on the appropriate limits. In the asymptotic limit, since we are working with asymptotically flat spacetimes, we recovered the Euclidean result for the curvature of circumferences, which is positive, and it goes to 0 from positive values. When we are in the horizon, for black hole spacetimes, you have to consider the horizon limit. And in the horizon limit, the geodesic curvature is minus the surface gravity of the black hole, and since we are considering non-extremal black hole, this will be a negative quantity. For the case of horizonless compact objects, we are to consider the origin limit, and at the origin for horizonless compact objects, the geodesic curvature diverges. Now we can try to construct functions that obey these asymptotic limits to try to count the numbers of zeros they have. Let's start with the black holes. So we know that we have a function that goes to 0 from above at infinity and starts from a negative value at the horizon. So it will have to have at least one zero, which is crossed with positive slope and will correspond to the usual unstable light ring. And if we want to have further zeros, they will have alternating stability, and they will always come in pairs, meaning that for this kind of spacetimes, we'll have an unstable light ring close to the horizon, then a stable one, unstable one, and so on until we end at an unstable light ring. This is different for the case of horizonless compact objects because at the origin the geodesic curvature diverges, which means that we can be in a spacetime where with no light rings because the function is positive both at the origin and at infinity. And if we want to have light rings, they will come in pairs, the innermost one being stable and the outermost one being unstable. Now we can start to considering this Timelike geodesics using the same methods as before. The Timelike geodesics are qualitatively different from null circular geodesics, the light rings, because light rings exist isolated, whereas Timelike circular orbs exist for a range of radial coordinates. So we have to try to find a special Timelike circular orbit which you can define by a single radius. This will be the marginally stable circular orbit which divides the regions of different stability for these Timelike circular orbits, as George mentioned before. So we are going to study the marginally stable circular orbits. So they are circular, so they have constant radial coordinate. They are orbits, so they have vanishing geodesic curvature. And they are marginally stable, so the Gaussian curvature must also vanish along that geodesic. These last two equations can be solved for the two unknowns we have, which are the energy of the orbit and the location of and the radius of the orbit. If we first solve the geodesic condition, what we obtain is the expression for the squared energy of that particle, of a particle orbiting at a given radius. We want this to be positive because we have the square of a real number here, and this will give us the allowed regions where Timelike circular orbits are possible. Well, the numerator will always be positive, so we don't have to worry about that, positive outside the horizon. But the numerator will vanish at the light rings. This means that at the light rings, the energy will diverge, and it will change sign when we cross the light ring. So if we have a stable light ring, what we have is this. Radially below the stable light ring, the square of the energy is positive, and we can have Timelike circular orbits. Radially above, the square of the energy is negative, and we don't have time-like circular orbits. What we have instead are space-like circular orbits, which have no astrophysical meaning. This goes, again, this agrees with what George said before, but it would be what would be strange is that if it didn't, then I would be worried. So we can insert this result for the energy on the expression for the Gaussian curvature. And what we get is essentially a product of three different terms. The first one will be always positive outside the horizon. The second one will vanish at the light rings, which is expected because the Gaussian curvature goes like 1 over epsilon squared, and the epsilon squared diverges at the light rings. And the final term will give us what we want, which are the marginally stable circular orbits. Well, the fact that this yields the light rings also is undesirable, so we have to look further into the light rings to see what else can we get from this. And what we notice is that when Gaussian curvature vanishes at the light rings, it always does so with negative slope. This means that we will always have an odd number of marginally stable circular orbits between two light rings, because if a function crosses twice with negative slope, it has to cross once with positive slope, and that zero will be a marginally stable circular orbit. Yes, that's what I said. So to know where the marginally stable circular orbits are, we have to once more look at the appropriate limits. In the asymptotic limit, we have the same result as in the null geodesic case, where it goes to zero from above. And in the horizon limit, we have this expression here, which is also positive everywhere else, which is also positive because the f prime must be positive at the horizon. So now we can once more look what kind of functions match these asymptotic behaviors. And this is the simplest case. And at first glance, since we have two positive limits, one might think that, well, we can have no marginally stable circular orbits, and this function can be always positive. But as I showed before, we always need to have one light ring at which the Gaussian curvature also vanishes. And it does so with negative slope, which means that we will have at least one marginally stable circular orbit. This is just the simplest case with the smallest number of light rings and marginally stable circular orbits. We can have more convoluted structure for time-like circular orbits like this one, which is a spacetime with 3 light rings, but I will not lose much time explaining this. And now we have horizonless compact objects. This is more subtle because the origin limit will depend on this coefficient f2, which comes from the Taylor series expansion at the origin of the GTT component of the metric. And if f2 is positive, then the Gaussian curvature will diverge to plus infinity, and f2 is negative, it will diverge to minus infinity. And this coefficient f2 is related to the 0, 0 component of the Ricci tensor at the origin, and this determines if the strong energy condition is obeyed or violated by the solutions. So we have to consider the two cases separately. For the case of solutions that obey the strong energy condition, near the origin, time-like circular orbits are stable, which means that we can have a spacetime with stable time-like circular orbits everywhere and no marginally stable circular orbits. However, if the strong energy condition is violated near the origin, the orbits near the origin will be unstable, meaning that we have to have at least one marginally stable circular orbit. So, in a nutshell, what I have done so far is, in general, I show that there are no time-like circular orbits between a stable and an unstable light ring, and that there will always be 2n+1 marginally stable circular orbits between an unstable light ring and a stable one, or infinity. For black holes, I showed that there are no time-like circular orbits between the horizon and the first light ring, and that time-like black holes always possess 2n+1 marginally stable circular orbits between the outermost light ring, which is unstable, and infinity. For the case of horizonless compact objects, I show that if the strong energy condition is satisfied, we have stable time-like circular orbits near the origin, and we can have spacetime with no marginally stable circular orbit. And if the sec is violated, then the time-like circular orbits near the origin are unstable, and we have to have at least one MSCO. Well, this is very simple and very beautiful, but this is just for the static case and spherically symmetric. We want, before I move on, I just want to remark that this is completely theory agnostic and does not depend on any on any field equations or anything. It just relies on the fact that we have a metric theory of gravity, such that gravity is defined by a metric tensor in a sort. So now I will try to put a spin on the formalism and consider rotating spacetimes and see what we can extract. So I will drop the staticity and spherical symmetry in favor of stationarity and axial symmetry, impose the additional constraint of circularity, and what we end up is this general line element with this odd term that we didn't have before, which is off diagonal, and will give us a lot of problems if we try to do the same thing we did before. But what changes with spin is that now with spin, geodesics are not necessarily planar, so we cannot constrain them to be on the equatorial plane of the spacetime. In particular, for the case of null geodesics, we can have geodesics with constant radial coordinate which have motion along the theta direction. These are so-called the spherical photon orbits, and they will happen for a range of radial coordinates. So we are not looking anymore for isolated solutions that we did in the static case. This is the example for Kerr, which is where we have this region with null spherical geodesics bounded by two light rings in black. So the goal is to use the same tools as before to determine the region where these spherical photon orbits can happen. And since this is ongoing work, I will focus only on the Kerr case as a proof of concept. Okay, so if we try to do the same thing as we did before, we notice that we have this term, which is linear in the momentum, which makes it impossible to cast this equation in this form here. Furthermore, there is no reason to a priori constrain the motion to be on the equatorial plane of the spacetime. So what we have to do is use all the symmetries of the spacetime, both the time-like Killing vector field and the vector field associated with the axial symmetry, input this in the Hamilton-Jacobi equation, and what we end up is this expression here, where capital A and capital B are either R or theta. This now can be rearranged in the desired form when we have this new metric contracted with the momenta. And this is, yes, I will only consider the massless limit, that's why the mass disappeared there. And this now we have this effective 2D metric, which can be used to define an effective 2D line element, which is Riemannian, bidimensional, and it is defined on the r theta plane of the spacetime. And the geodesics of this manifold, of this bidimensional manifold, will be the projection of the spacetime geodesics onto this plane, the r theta plane. And now it depends on both the energy and angular momentum, but we can absorb the energy so that it will depend only on the impact parameter of the geodesics. Now I will consider the simplest example, which is Kerr. This is very famous metric, the only metric by Chandrasekhar. And if we insert this metric on the expression for the effective metric, what we end up is something with this shape where f and g depend only on one of the coordinates and have these simple expressions here. And what is interesting is that this has precisely a Liouville form. That is, it is a metric on a Liouville surface. And Liouville surface have this general form, which consists of a conformal factor of a sum of two functions which depend on only one of the coordinates. Why am I telling you this? Because these metrics are very special. They have a conserved quantity along geodesic motion, which is related to a non-reducible rank 2 Killing tensor. Okay, and it has this expression here. This is a non-trivial constant of motion, and we know that the Kerr spacetime also has a non-trivial constant of motion, the Carter's constant. And what we see is that this constant of motion for our effective 2D metric is precisely Carter's separation constant, as we hoped. But this is some This is something else. This is just a caveat, because what we are interested in are the spherical photon orbits, which must satisfy this geodesic condition. And for our metric, it has this form. And so for these two vanishes, either the first term vanishes, which is between square brackets, or the second one does. So we have two classes of solution for the impact parameter, the first class and the second class. What we do now is that we want the metric to be Riemannian, and this Riemannian character of the metric will be determined by the conformal factor. So we insert the solutions on this conformal factor, and what we see is that the second class will always be negative. So these metrics will always be non-Riemannian, so they are unphysical. And we see that the first class has this expression here, which can be either positive or negative. So what we do now is study this class and plot it on the r theta plane. And what we obtain is this for Kerr with the spin parameter of 0.99. And we have this region in green where the conformal factor is positive and we have Riemannian metrics. And outside this region, the conformal factor is negative and the metrics are non-Riemannian, hence unphysical. And this is precisely the result we know from Kerr. This is some kind of weird plot. I will try to illustrate what this means. Is that for any radial coordinate, if it is contained in this green region, at every radial coordinate we have a spherical photon orbit that ranges between minus theta star and plus theta star, and this region will be bounded by the two light rings when the variation in theta is 0. So, to close, I accomplished the goal I set to myself before I start the second part, when we recovered the results from Kerr from this effective 2D metric. And hopefully this can be used to establish some theorems, generic theorems like we saw from Pedro concerning now spherical photon orbits, or even Timelike circular orbits for Kerr. And it's still, I am still unsure how the Gaussian curvature relates to this metric, so if you have any idea, please tell me now. Thank you.
Thank you, Pedro. João, sorry. Do you have any questions online?
João, so this, in particular, can you show some of the details in the last part? Unfortunately, it was a little bit too fast. So you have this conformal factor that you say that is that it changes sign, and so there's this different signature. That is the point. So how do you connect these with the spherical photon orbits? So you can realize that for Kerr, that this is indeed connected. You can recognize the shape, but how can you say for sure that it is connected generically with these spherical photon orbits? Yeah, in this part it was a little bit too fast, I guess, to understand that detail, but do you have any comments on this?
Yes. It is related because it is a solution for the geodesic condition. So we insert here the impact parameters for spherical photon orbits. That's why they are related. And for this, so we insert, it's like I showed you before for the static case when we solve the geodesic condition for the energy, and it could be either, and we have epsilon square equals something which can be positive, zero, but positive, diverge, or be negative. So this is some sort of equivalent with that. We want the metric to be Riemannian. So that's why we have the spherical photon orbits. I'm not sure if this answers your question, but...
Well, I'm not sure if I fully understood if that fully addresses my question, but we can discuss more later. I want to discuss more later.
We solve this expression here,
yes,
because we want to have curves with constant radial coordinate,
yes,
which are geodesic, so their geodesic curvature must vanish. We solve this for the impact parameter. We feed the impact parameter back to the metric, and we impose the metric to be Riemannian.
Okay. But you are forcing there a constant radial coordinate. That's a critical
Yes.
part.
Yes, because
okay.
that's what we are interested in.
Okay, okay. Then, okay, I understand that.
This is more general than that, but this is the goal I was trying to reach.
Yeah, I'm in particular very fascinated if you don't impose that condition, but we can discuss later. Okay, see you.
Thank you. So, any more questions? No?
So, João, as you mentioned, the condition for the geodesics is from this geodesic curvature, and the Gaussian curvature is related to the stability, right?
Yes.
So it's very curious because from the Gauss-Bonnet theorem, you have precisely these two quantities. So the geodesic curvature plus the Gaussian curvature is equals to a topological invariant. So can you use this Gauss-Bonnet result to infer something about the stability or something like that?
Well, I worked a lot on the Gauss-Bonnet theorem because it is widely used in the literature to compute the deflection angle on this sort of space-times. You define a surface on the equatorial plane, and you can compute the deflection angle. But you are asking, well, you can. There is. I can go back to where I showed you some literature, because that was used in a paper by Gibbons, the Gauss-Bonnet theorem, to state, for example, which kind of geodesics are possible in a given space-time. It's this one. If you are interested in that,
Yeah,
I
okay.
recommend you go and check this paper by Gibbons and Warnick and this paper by Gibbons and Werner. They are quite comprehensive.
Yeah, okay. I was just curious because precisely these two quantities appear in the Gauss-Bonnet theorem, and
Yes,
they are equal to a topological invariant, so perhaps
Yes,
this
but
can be useful.
Yes, but then you would have to define a surface where we are integrated, and that's it. You have to know what you are looking for when we are defining the surface. But in principle, you can use this to study properties of the space-time. Yes.
Yeah, thanks.
So,
So thank you for the very nice talk. So I think that I just want to make a quickly comment, because you said that the setup that you use is quite general, right? You do not assume field equations, nothing like that. But I would like to point out that, in fact, I think that there is a key assumption, that is the fact that the photons follow new geodesics of the standard geometry. They are related with linear electrodynamics. So what I want to say that if you suppose that the photons associate with, for instance, nonlinear electrodynamics model, they will follow a different geometry that's different of the geometry that you showed there. So in these cases, I think that we can very different results.
But do the photons not follow geodesics?
No, they follow new geodesics, but of a different geometry. That's different of the geometry that you are showing there.
But how is it different?
Because they are related with a different electrodynamics. And so in this case,
Yes, but in the end, you have a four-dimensional manifold, right?
Yes.
So you can always cast it in that form. If the conditions I showed you are obeyed, it can always be cast in that form. Probably the general solutions are not in that form, but you can redefine them to have them in that form. The only assumption is that you have a four-dimensional space-time, and the particles will travel along the geodesics of that four-dimensional space-time. Nothing else. This is not Schwarzschild, Reissner-Nordström, general relativity. This is, if you have a manifold and you are studying its geodesics, this is it.
Okay. Now I think that I see better. So thank you for.
No problem.
Thank you, João, for the mini course, especially. Just kidding. But I have a naive, perhaps, question. If you were just saying now, my assumptions don't rely on any specific spacetime, for instance. So if I give you a problem with less symmetries than the one that we heard from Pedro, from George, so something in which only you have a Timelike killing vector, and for instance, you don't have anymore an angular momentum that is well defined, could you instead, could this method be complementary and give you some more information than just solving a very complicated geodesic coupled equation, or is precisely equivalent to that and you will not get any information more?
Well, if you have less symmetries and you only project along the killing symmetries of the spacetime, you would have, well, in particular, if you have a conserved energy associated with a Timelike killing vector field, you would have a Riemannian three-dimensional metric or a three-dimensional manifold, which can also be studied. It's not so simple as the surface case, but in that case, well, solving the whole problem might be very difficult, but if you focus on hypersurfaces of constant other coordinates, then we can use the same mechanism, the methodology I presented here. You just have to, but then the limits would change, but you would still have a b-dimensional manifold whose geodesics correspond to the geodesics of the spacetime. And this is in a way simpler because this is the simplest surface you can have. It's only 2 dimensions, and this is very well known by mathematicians, and it's Riemannian, which is also simpler than Lorentzian signature. But I think the information is the same. This does not provide any new information. It only provides a new way of looking at the information and a new interpretation of the information. But I would assume that you have a very specific problem in mind, so.
I do. Okay, no, but thank you. I mean, it's because the degree of information is going to be the same, and that's fine. But if you have to solve a completely coupled system of equation, it might be way harder. So if your method employs some differential geometry concept that can ease that part, you have the same information, but it's going to be more clear. That's why I'm interested if this can be applied.
I'm not an expert, but I would say that there are possibly ways to simplify that analysis, because mathematicians have been studying this kind of structures for a long time, so they have a lot of theorems concerning the existence and properties of such surfaces, which is not the case for Lorentzian 1 plus 2 dimensional spacetimes.
I see. Thank you very much.
So I think we can finish here. Let's thank the speaker again.